Yeah, hello everyone. My mentee Boran Karagöl, who is from Hacettepe University, and we had an opportunity to concentrate on perturbation methods, and he will give us his presentation during this session. Yeah, Boran, we are listening to you. Thank you.
All right. The topic I will be presenting is the perturbation methods. So what is perturbation theory and what is it good for? Perturbation methods provide powerful techniques for obtaining approximate solutions to various equations in mathematics. For any given equation, we can introduce a small parameter epsilon, which in turn helps us to obtain an approximate solution that may or may not converge to the actual solution of the original equation. And what I mean by convergence here is that we'll usually assume a solution in the form of a series. So we'll have to look at the convergence of that. Obtaining approximate solutions within a controlled error margin through perturbative methods does usually involve less computer time than evaluating the exact answer. And we'll see an example of that in a minute or two. And to add more to that second statement, this way of obtaining solutions is heavily used in quantum mechanics physics, especially in the Schrödinger equation. So here we have a differential equation, Poe oscillator equation, and this equation tends to an oscillation regardless of the initial conditions. And here we can see a graph, horizontal line representing the k values and the vertical line representing the period of the oscillation. And if you were to try to get values of that, depending on k, numerical methods work best between the values 4 and 10, and they quickly lose their accuracy between extreme values. So that's where the perturbative methods take over, as you can see here. As k tends to 0, here we have an asymptotic approximation with this dotted line, as you can see right here. And as k goes to infinity, we also have another asymptotic approximation. And this is really useful because if for any given differential equation which you do not know how to exactly solve or get the exact answer, you can find approximate asymptotic approximations which give you an idea of what the solution might actually look like and give you an intuition of what the solution actually looks like. The first method we'll take a look at is the iterative method. Here we have a quadratic with the epsilon coefficient. This is a really small coefficient. Rewriting in iterative form and looking for only for the positive root, we get this, and it's rather simple to get. You just toss the last two terms to the side and square root both, since we're looking for the positive root. And the reason why we call this xn here, we think of it has an epsilon coefficient, so we think of it as a small correction to get the next iteration in the x. To find the starting point for x0, we set epsilon to 0, and we get the starting point, x0 equals 1. Then we get the next, through the iteration, we get the next value, x1 equals this. And if we were to expand that by binomial series, we get this. And you can manually check if these terms correspond with the actual solution. Only two terms here actually correspond with the solution, and there's a rigorous reason why that is, but I did not prefer to talk about that. So we only take into account the first two terms and apply the iteration, and we get x2. And to get the x3, we only take into account the first three terms, and so on. Again, there's a rigorous reason why we do that, but I do not prefer to talk about it. By applying the iteration, we can obtain the exact solution term by term, as you can see here. It's the same thing here. And these binomial expressions converge. It has a convergence radius. So the next method is the expansion method. The most common method used in the perturbation methods is the expansion method. Here's a method for algebraic equations. We first assume a solution in the form of a series, then substitute that into the given equation. Then we match the powers of epsilon and find the values for x0, x1, and so on. And if we were to try to solve the earlier example with the expansion method, we substitute this series into the x, and we multiply, and we get a polynomial with the coefficients of epsilon. And since we have to set the coefficients of epsilon to 0, we get the starting point x1 equals 0. This is the coefficient of epsilon to the power of 1. It also has to equal to 0, so we get x1. And this is epsilon squared, so we get x2, and so on. And we get the exact solution this way. And what is so useful about this way of obtaining an answer is that if you were to actually try to compute the exact answer of this compared to finding a solution like this, it requires more running time for the computer. So it's a lot more efficient to actually use this method to obtain exact answers, as seen here. By the fourth term, for epsilon equals 1.6, by the fourth term, we get pretty close to the exact answer. So it requires less running time to use the expansion method. So here's another important application. Let's take a look at how the expansion method applies to differential equations. Here we have a differential equation with the given initial conditions. To solve this equation, we introduce a small parameter to the equation, and epsilon, and we assume a solution in the form of a series. Now, you might ask, how can we always assume a solution in this form? And I'm not currently equipped with the mathematical knowledge to answer this in a rigorous way, but there is a rigorous way to answer this. But here's the intuition on that. Suppose you have a differential equation, right? And the solution of this differential equation is actually close to a special system, like harmonic or something. So you introduce a small parameter to that equation, and maybe as that epsilon varies over small values, the solution gets satisfied. So when obtaining the exact answer with the epsilon, you maybe expand that solution through Taylor series using the powers of epsilon. So that's one way of thinking about it. And maybe if you're lucky and the series actually converges for epsilon equals 1 to the exact solution, then you get the exact answer. And we'll see an example of that in a minute. And since because of the initial conditions, y ends 0, it has to be equal to 0. It's the same thing with the derivative. Setting epsilon equals 0, we get the y0, which is the starting point for the series. We get 1 plus x. And if we were to substitute this series into the equation, we would get this, which is an iterative thing. You can actually substitute that and take the derivative and find this out yourself. It's really simple. You just have to match the powers of epsilon, which allows us to express the solution iteratively. So we integrate it twice, and we get the general iterative expression for the y-ends. And since we know what y0 is equal to, then we can get y1, y2, and so on. And it's easy to show that here's the general solution, by the way. It's easy to show that when n is large, the nth term in the series will be bounded by the absolute value by this. So here k is the upper bound for the function ft. Thus, the series converges for all x, and also if x squared times k is smaller than the perturbation series is rapidly convergent for epsilon equals 1. And an accurate solution to the original problem may be achieved by taking only few terms. So here we substitute that fx with a exponential function, and we find the exact solution for epsilon equals 1 for small values, of course. And here's the graph of that. The exact solution of this differential equation is expressed in the Bessel functions, and it's a long expression, so it's really difficult to get that exact solution. But through perturbative methods, as you can see, by the fourth term perturbation series approximation, we get so close to the exact solution. So it's really powerful. Whereas if you try to find a solution via a normal series method in the differential equations, you assume a solution in the form of a series and find the convergence and so on. It's really far off, and this is only the 11th term of the series, so it's really far off. Compared to Taylor series approximation, perturbation series converges for all x bigger than 0, perturbation solution exists even if there is no Taylor series solution. So it is a really powerful method. So here we move on to the regular and singular perturbation. In order to understand the difference between the two, let's take a look at the given quadratic. If we were to set the epsilon to be equal to 0, as we did in the last example, we would only get one root, which is inconsistent because we know this quadratic to have two solutions. So how can we obtain the other root? By taking a look at the exact answer, we'll figure that out. As we said, this is the exact solution. As we set epsilon equals 0, we see that a solution evaporates off to infinity. So setting epsilon equals 0 is not going to work. This is an example of a singular perturbation problem in which the limit point epsilon equals 0 differs in an important way from the approach to the limit as epsilon goes to 0. To find the leading order term, we must take a look at the dominant balance in the equation as epsilon goes to 0. And what I mean by the dominant balance in the equation is, if we were to go back, since we know this term contains the other root, it no longer becomes logical to neglect that term by setting epsilon equals 0. So what we have to do is we have to consider this as a dominant term and see how its magnitude relates to the other terms in the equation as epsilon goes to 0. And this whole equation has to equal to 0 as well. So here's an example. If epsilon x squared is asymptotic to 1 as epsilon goes to 0, then x has to be at least in the powers of epsilon to the power of 1 negative 1 divided by 2. But then the x term in the equation becomes the largest and is not balanced by another term, which is inconsistent because we want this term to be the dominant one. If x is asymptotic to 1 as epsilon goes to 0, we obtain the other, unperturbated root, which we already did. If epsilon x squared is asymptotic to x as epsilon goes to 0, then x has to be at least the power of epsilon to the negative x epsilon to the power of negative 1. This is consistent because the terms can balance each other, because these two balance each other. And it also suggests a scaling transformation in the form of this expression right here. And if we were to apply this transformation to the given quadratic, we would obtain a solution like this in the y's. And it has now just become a regular perturbation problem. Solving for the roots by setting epsilon to be equal to 0, we obtain the other root, the singular root, negative 1. And since we know y is equal to this, we get the starting point for the equation. It's the same. So that's how we do it. On example 3, it's the same idea. You have to compare terms to see what terms match each other. A and B, you don't get good results. Speaking for C, we do the same thing and figure out that these two terms, if these two terms are asymptotic, then it is consistent because we get the powers of epsilon to the power of negative 2, and that is also bigger than the other dominant term. So these two terms become dominant and they can balance each other. So this also suggests a scaling transformation in the form of this. And if you were to substitute that in there, and you would get that. And setting epsilon equals 0, we get the other single root, and we get the starting point for the single root. And there's one thing to note here it's that when you assume, we have always assumed a series solution in the form of integral powers of epsilon, right? In epsilon 1, epsilon squared, epsilon cubed, and so on. But in here, you need to assume a series solution in the form of a rational power, because if you didn't, then the terms wouldn't match each other, right? If you tried epsilon 1, epsilon 2, and so on, you would not be able to find matching terms because of these powers right here. So that's that. Find the approximate solution for this differential equation with the boundary value problem. It's a boundary value problem. This is a singular perturbation problem because the unperturbated equation y dot equals 0 does not satisfy the boundary conditions. As we did in the last examples, if we were to try to set these epsilon to be equal to 0, then we would get a constant function y equals c, which does not satisfy the boundary value problem. So it doesn't work. It's a singular perturbation problem. And in order to obtain a starting point for the y0, to get the y0, the 0th order term, in order to find the 0th order term, techniques such as asymptotic matching and WKB theory must be used. And these topics are a bit above my head, so I do not prefer to talk about those. So, and that concludes my presentation. If anyone has any questions.